Okay, good morning, everyone. Let's just go ahead and get started. Um, I have posted information regarding midterm number two, and so that will be 1 week from today on November 13th. So I will send out a seating chart again, and um, and we'll take it in class in person. So. Uh, Exam is pencil and paper. We'll take it in class. I'll try to. You should be able to complete it in about 45 minutes, with around 5 minutes for passing out papers and collecting stuff. I try to get everything set up so you'll have as much time as possible. But that's the idea. I'll create a scene chart, and so just be on the lookout for that. Um, Monday is a holiday, so you'll have I guess, a little bit of. So I won't see you Monday. It'll just, I guess, Friday. I'll see you Friday, and then when we come back on Wednesday, we'll be taking the exam. Okay, you'll be allowed to have a sheet of notes and handwritten or typed, same kind of rules. Make sure you put your name on it, and then I'll collect the note sheet in with your exam. Okay. And then make sure you bring a calculator. Okay. Um, all right. So these are the problems that I have in mind. One will be convolutions. So you'll probably want to write down a few notes from the convolutions lecture, and I'll provide kind of a random sample of some uniform or normal values, and and just for simplicity, I'll round them off to a couple places after the decimal, so you're not going to have huge huge values to or like a whole bunch of decimal places to work with. But anyway, you'll take those and use some kind of convolution to make another random value. So like if I give you uniform values and I say, hey, we've got a binomial distribution, then you'd convert them into zeros and ones and count how many ones you have and things like that, right? Um, uh, there you might have some of these things, for example, like the gamma distribution is a ratio of exponential values. And so for the exponential things, I'm not going to give you exponential values. I'll give you either uniform or random normal. And so you might have to use like inverse CDF method to go from uniform to random uniform to random exponential. And so, just make sure you know how to do something like that. This should be a relatively easy problem. It's not going to be worth a ton of points. Um, but yeah, so should be hope the hope is that it will be straightforward. Okay. Um, and then we'll have a problem with rejection sampling. Okay, and then for rejection sampling, I will provide a some kind of target distribution, the desired distribution that you want to generate values or samples from. I will provide another distribution that will be the proposal distribution. So I'll give you the PDFs of each of these things. Um, and then for rejection sampling, remember you multiply the proposal distribution by some constant m, so that the proposal distribution times m is greater than or equal to the target distribution at all locations in the support of x, or support of the distribution. And so you'll have to figure out the optimal value of m, which is uh, described in the notes. Um, and then once you figure that out, I'm going to provide some random values. So I will provide random values generated by the proposal distribution. And then going along with each of those random values generated by the proposal distribution, I'll provide a random uniform value that you will use to decide whether or not to accept or reject the proposed value. Okay. And So that's that. Okay. So you'll figure out the acceptance ratio, the acceptance value R, and then you'll tell me if this proposed value should be accepted or not based on the random U I provide. Okay. Um, then you will also have a Metropolis algorithm problem, a discrete case, and a continuous case. So the Metropolis algorithm, discrete case, so we did an example with like the island hopping. So it'll be kind of like that, but not not going to be the same as the island hopping. Okay. So there will be some arbitrary target PMF, a distribution over discrete states, and then I will specify how the proposal distribution will work. Okay. So like in the island hopping example, you flipped a coin and you had a 50% probability of going to the right or to the left or something like that. And there will be some kind of description of how um, the proposal distribution would work. And then after that, you'll figure out, so based on the information provided, you'll have to figure out your transition probability matrix P. What's the probability of transitioning from one state to another state? And then, given the distribution at time t, I'll ask you to find the distribution at the next iteration at time t plus one, and that will be that. Okay, and then the last problem will be Metropolis algorithm for the continuous case, and for that, I will provide an arbitrary PDF target distribution. And then I'll also provide a uh, proposal distribution. And the proposal distribution will be a um, normal distribution, okay, centered at your current location. And then I'll give you some arbitrary starting location. And then you'll perform, yeah, probably around 2 iterations of the Metropolis algorithm. And for each iteration, I'll provide random uniform values. Okay. So, you know, U1, you'll use U1 and inverse CDF method to find the proposed value of X. So I will give you the normal CDF table. So these are all like with this description, you should be able to do this yourself. Okay. Um, and you can try this out. So I'm going to give you a random uniform value between 0 and 1. And then from that, you'll use a normal distribution table, normal CDF, to perform inverse CDF method to figure out what value is being proposed. And then once you have the value proposed, you're going to figure out P move, and then you'll decide whether or not to um, accept the proposed value. Okay. And you'll do that. So that requires uh, running the Metropolis algorithm. Okay. All right. So that's your description of your second midterm exam. Um, should be, I don't know, should be okay, I think. Um, yeah, so we'll have that. Okay, let me pull up these notes. So these notes are handwritten and this is just kind of I guess a derivation or maybe a proof to show how that the Metropolis Hastings algorithm does work as far as generating values from the desired target distribution. So these are also available right here. Okay. Oh, you know what? I have forgotten to create a lecture view quiz. Give me a second. Okay, so I think uh, the lecture view quiz is now available, and yeah, your first answer is the letter B. B as in bear. B is your first view quiz answer. Okay, the letter B. Okay, all right. So let me cover the Metropolis Hastings algorithm. So the Metropolis Hastings algorithm is a generalization of the Metropolis algorithm. Um, the difference between the Metropolis Hastings algorithm and the Metropolis algorithm is that for the Metropolis algorithm, your proposal distribution must be symmetric. So the probability of proposing, so here I've got two locations on the number line, x at time t and x prime. And the idea is if you will have a proposal distribution and you're currently located at x at time t, what is the probability of proposing x prime? Okay, you have some kind of value. And then for it to be symmetric, so the probability of um, getting x prime given that you're at xt is going to be the same as the probability of basically proposing xt if you are centered at x prime or if your starting location is x prime. So in this diagram, I have the normal distribution, and this is symmetric, that if you have a normal distribution with mean xt and you're located at x prime, the distance from xt to x prime, whatever that difference is, if you take the negative side, it's the same probability there. So the probability of proposing xt if you are currently at x prime is the same as the proposing x prime if you're currently at xt. Um, with the island hopping example, we used a fair coin and we flipped it. And so if you're currently at state 3, the probability of proposing state 4 is 50%. And if you're currently at state 4, the probability of proposing state 3, is also 50% because, if you get heads, you propose to the right. If you get tails, you propose to the left or whatever we said it was. Um, that's how we have it set up. Um, the Metropolis Hastings algorithm is a generalization of this and does not require the proposal distribution to be symmetric. Okay, it does not require it to be symmetric. So it would be as if you had a weighted coin. So if you're on the island hopping example, and let's say you had a coin and it landed heads more frequently than it landed tails. Let's say it landed heads 60% of the time. And so, you propose the island to the right 60% of the time, and you propose the island to the left only 40% of the time, or something like that. Would that still work? Okay. And the answer is, yeah, with the Metropolis Hastings algorithm, you just you change the acceptance ratio, the acceptance probability, um, to factor that in. Okay. And so this part is very, very similar to the Metropolis algorithm. It's just your acceptance probability now factors in, what is the difference in proposal probabilities? If we're currently at, x prime, what's the probability I propose xt? How is that different from proposing x prime if I'm wait, what was it? Uh, what's the probability of proposing xt if I'm currently at x prime versus what's the probability I propose x prime if I'm at xt? Okay, so but the steps of running the Metropolis Hastings algorithm are pretty much the same as running the Metropolis algorithm. It's just how you calculate this acceptance probability um, is just adjusted. Okay, so you start some initial start value x at time 0, and again, um, it you can start at pretty much any location within the support of x, and we saw that um, you know in Monday's example. I said, I want to generate values from the normal distribution, and so these are Monday's notes. And I said, I want to start at some terrible location like 100, okay? Even though our target distribution was a normal distribution centered at 15. And so, you could start at a, a terrible location, but eventually, because of the Metropolis algorithm, it will eventually get to kind of where it's supposed to be, and then it will generate values from there. So just pick some initial value. As long as it's within the support of X, you'll be okay. You have some target distribution P, and really you just need a function that is proportional. Okay, so if the target distribution P, if you don't have that directly known, you can just use F. Again, F just needs to be proportional to P, your PDF, which is whoops, what we did over here. We just needed something proportional to it. So this had some normalizing constant 1 over sigma root 2 pi. And here, that's just a normalizing constant. So, you could do without it. And the same applies here. Here I have P written, but if you want to just use F, that's okay. So your acceptance probability, this is how it changes. So with the acceptance probability, it was the probability of X proposed divided by the probability of X current, which here we're calling X proposed X prime, and the X current is XT. So the probability that you move with the Metropolis algorithm is um, or just right here, okay? F of X proposed, F of X proposed or P of X proposed divided by F at your current value, F at X at time T, okay? Which is basically what we have here. But here we're going to multiply it by the fact that the probability of proposing things is a little bit different, right? That perhaps flipping heads is not, it doesn't have the same probability as flipping tails. And so we have that factored in here. What's the probability of proposing location xt if you're currently at x prime versus what's the probability of proposing x prime if you're at xt? And you can see for the Metropolis algorithm, these two things are equal to each other. So this part just becomes 1, right? So in the Metropolis algorithm, the proposal thing, g of xt given x prime divided by g of x prime given xt, that's just 1. So this thing, this probability min of 1 of p of x over p of x proposed divided by p of xt is just the same as, is exactly what we have here. So, and then so once you have that value calculated, then you will either accept or reject that. You'll generate a random u between 0 and 1. If u is less than this p move, then you'll accept the proposed location. X prime becomes x at time t plus 1. And if u is greater than p move, then you'll reject it. And your current value, x at time t, gets reused for x at time t plus 1. Okay, so that part is the same as the Metropolis algorithm. So you'll take x proposed, set it to x at time t plus 1. Otherwise, set xt equal to x at time t plus 1. All right, so the Metropolis-Hastings algorithm, just a generalization of the Metropolis algorithm, and it works by just kind of changing this acceptance probability by factoring in the difference between the probability of proposing, proposing a new value if it's not the same. Okay, so how do we show that this is going to work? Okay, and the idea here is that the Metropolis-Hastings algorithm is going to work because there's going to be detailed balance at the target distribution. That for any two states that you pick, x, we'll call it xt and x prime, okay, that the amount flowing from xt to x prime is exactly equal to the amount flowing from x prime to xt. The way this is drawn, you think of, it seems like it's a discrete distribution, but um, but it also generalizes to a continuous distribution that if you pick any two locations on the number line or within the support of x, okay, you can show that you have detailed balance between those two locations. So um, that wherever your state space is, you pick any two states in Metropolis, the Metropolis Hastings algorithm, and the Metropolis algorithm, which is just a special case of this. You can show that you have detailed balance, that the amount flowing from this state to the proposed state would be exactly the same as if you had flipped it around. And what's the amount flowing from this location, the proposed state, back to the x at time t. Okay, and this will be true for any two states if all of the states follow that target distribution p of x. Okay, so the probability of being in state x um, in the target distribution, that's going to be this probability of p of x, and then we have the probability of kind of transitioning from state x at time t to x prime. Okay, so this will be that what's the probability that if you're currently at xt, what's the probability of transitioning to x prime? And so to show that we have detailed balance, we need to show that the amount flowing from xt to x prime is the same as the amount flowing from x prime to xt. Okay, so um, so the amount flowing from xt to x prime is the probability of starting at x state xt, and then we're going to multiply it by the probability of, okay, well, if you're there, what's the probability that you'll then go to x prime? So we're going to basically multiply these two things together, probability of xt times the probability of x prime given xt. And what we want to show is that that's exactly equal to the amount flowing in the other direction. So we're going to have to figure out, okay, well, what's the probability of starting at x prime? And then what's the probability of then transitioning from x prime to xt? So that will be the probability of x prime multiplied by the probability of xt given x prime. Okay. Um, so the trivial case is if your proposed location is rejected, then the next state, right, is the proposed state is, I mean, the next state is the current state. So, um, you know, then you're just, I guess things are flowing to itself. Okay, so things are flowing to itself, and so therefore, um, both sides are obviously equal because the next state x prime and your is the current state. So, um, so then you've rejected the proposed location. So you know the amount flowing to itself is the same is equal to the amount flowing to itself. Um, so that's the trivial case. Okay, but what we'll show is that if you have two different locations, that the amount flowing from kind of your current location to the proposed location is going to be the same as the proposed location to the current location, or basically just location one and location two, or location t and location prime is the same as the amount flowing from location prime to location t. Okay, so um, what we will do is we'll look at the left side, okay? And then we'll show that that is exactly equal to the right side. So the left side is going to be the amount flowing from t to x prime. So that's going to be the probability of x being at xt multiplied by the probability of going from xt to x prime. And then we want to show that equal to the right side, which is the probability of being at x prime multiplied by the probability of going from x prime to xt. So we'll start with the left side, and then we'll show that it is equal to the right side. So um, this probability of xt, okay, is going to the left side is probability of xt multiplied by the probability of um, flowing from x prime to xt to x prime. Okay, and so the probability of going from x this quantity, the probability of x prime given xt, is equal to the minimum of 1 and x prime over x, this is the quantity given by the Metropolis Hastings algorithm. It's this quantity right here. Okay. So this is what we're going to do. Okay. And then what I'm going to do is I'm going to um, distribute, I'm going to multiply, um, I'm going to multiply this quantity, g of x prime given xt. I'm going to multiply it through this minimum function. Okay. So this okay, sorry. The probability of this um is first we have to propose it, and then this is the acceptance probability, right? So the amount kind of going from xt to x prime is the probability of proposing it times the acceptance probability. Okay. And what we're going to do is we're going to multiply the probability of proposing x prime given xt. I'm going to distribute that through the minimum function. And then in the minimum function, this one, we're going to just replace it with probability of xt divided by the probability of xt. So that's going to be that. Okay. So this is the probability of going from xt to x prime. We have to propose x prime, and then we have to accept x prime. This is the acceptance probability here. Okay. So when I distribute this, I'm going to take the minimum between 1, which is now the probability of xt divided by the probability of xt times the probability of proposing x prime given xt. Okay. And then I multiply the quantity after the comma, the minimum there, by the proposal probability, which is g of x prime given xt. Okay. And that's going to cancel out with the denominator there. All right. So, and then I will distribute the probability of xt through the minimum function. And so when I do that, now we need to get what is the minimum. Okay. Here I'm going to have probability of xt divided by the probability of xt. We're multiplying it by the probability of xt. So this quantity cancels with this quantity down here. And we're going to be left with the probability of xt times g of x prime given xt. Over here, this probability of xt cancels with this probability of xt right here. Okay. And then so I've got g of x prime, or probability of x prime, times what's the probability of proposing xt given x prime. So I got g of xt given x prime. So the left-hand side, the amount flowing, basically the amount flowing from xt to x prime is going to be the minimum between these two quantities. So we have this quantity, probability of xt, g of x prime given xt, probability of x prime times g of xt given x prime. And whichever one of these quantities is smaller, the minimum of these two things, that's going to be the amount flowing from xt to x prime. Okay, so that's the left-hand side. On the right-hand side, we're going to do something very, very similar, except here we've got, what is the what's the amount flowing from x prime to xt? So we've got the probability of x prime multiplied by the probability of transitioning from x prime to xt. The probability of transitioning from x prime to xt is, first you have to propose it. So that's going to be g of xt given x prime multiplied by the acceptance probability. Okay, what is the probability that you will accept this proposed location of, or what's the probability that, yeah, you'll accept xt if you're currently at x prime. So if you kind of go through, what is the acceptance probability? So first you have to propose it, and then what's the acceptance probability? Now, assuming that you're currently at x prime and you want to transition to xt, it will be this. So it's the minimum between 1 and probability of xt divided by x prime, and then g of x prime given xt and g of xt given x prime. So it's kind of like the reverse. You're just switching the locations of x prime and xt. So on the left-hand side, we had x prime, p of x prime divided by xt, and over here we have p of xt divided by x prime, and then we have x prime given xt divided by xt given x prime. So we're just kind of swapping these labels because that's all we've done here. And so now, again, I'm going to distribute the proposal probability. What's the probability that I propose xt given if I'm currently at x prime? I distribute that through the min function. And so we get this, okay? And then again, this quantity over here is going to cancel out with this quantity. So I've got x xt over x prime, p of xt over x prime, and then multiplied by g of x prime given xt. Over here, we're replacing 1 with p of x prime divided by p of x prime. And so I have this multiplied by here, and then I'm going to distribute this. And so this x prime cancels with this p of x prime, and that cancels with this p of x prime. So we're left with p, the minimum of p of x prime times g of xt given x prime. So what's the probability I propose xt if I'm currently at x prime? And then over on the right-hand side, we're going to get what's the probability of xt um, if I and multiplied by the probability I propose x prime given xt. So on the right-hand side, we get, what's the minimum of this? So the amount flowing from x prime to xt is the minimum between these two quantities. And then the amount flowing from xt to x prime is the minimum between these two quantities. And we can see that these two things are exactly equal. That because here you have the minimum of these two quantities, and the two quantities are exactly the same. We have p of xt times g of x prime given xt, p of xt times g of x prime given xt, and then p of x prime times g of xt given x prime. So p of x prime times g of xt given x prime. All right, so this is just kind of mathematically working it out to show that these two quantities are exactly the same. All right, and this quantity again represents the amount flowing from state xt to state x prime. And over here, this is the amount flowing from state x prime to xt. And you can pick any two arbitrary states in the entire kind of state space of your Markov chain, and you'll find that this relationship holds, right? And whether your Markov chain is a discrete Markov chain and you have discrete locations, or even in the continuous case, okay? Even in the continuous case, you've got basically any two locations, you will find that this relationship holds. And so, in the continuous case, you've got infinitely many cases, or your state space has infinitely many states, okay? But even among all infinity of those states, you will have detailed balance here. And so in the long run, the probability of kind of flowing from one location to another is going to be exactly the same as the amount flowing in the other direction. And because the Markov chain is ergodic, it's irreducible. Every state can be reached from any other state, okay? And it's aperiodic and ergodic in that eventually it will reach a stationary distribution. When it reaches that stationary distribution, detailed balance will be achieved when every state follows, okay? The probability of being at any one of these states is equal to the probability in your target distribution. Okay, so once all of the states in your state space follow the target distribution, then you will have achieved detailed balance, where the amount flowing from one location to another is equal to the amount flowing in the opposite direction. Okay, I guess that's actually all I had planned for today. So a little bit of a shorter lecture. I'll just let you guys go a little early. The last, let's see. Let me check the answers. The remaining two answers to the view quiz today are the letters A and the letter D. Okay, A and D are your last two view quiz answers for today. And with that, we will go ahead and wrap up today's lecture. Take it easy for the rest of the day, and we'll see you on Friday.